Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad called 12th graders 2023, problem number 2. Let G be a group with neutral element E and let H and K be two different proper subgroups of G whose intersection is trivial, consists of only E. Suppose further that G minus H union K union E is closed under the operation of our group G. Prove that G squared equals E for every element G of our group G. It's a very nice problem, a bit unusual because it's from group theory, from higher algebra, but it's given to 12th graders, but it's Romania. Romanian Olympiads are very different. And a bit of terminology and hints, or maybe our plan for proving this theorem. We say that H is a proper subgroup of G if it is a subgroup and it's not equal to the entire group G. Some authors give a further constraint that it's not trivial, but I just take this definition that subgroup is proper if it's not the entire group, and we say that group containing only neutral element is a trivial subgroup of G. Also, in the original formulation of the problem, it was missing that H and K should be different. Our theorem is no longer true if both of them are trivial, so they must be different. And here is our plan. First, name our set G minus H union K union E, name it as L, capital L, and try to prove the following claims. They are building blocks of our proof. First claim, for every element L in our set L, L inverse is also in our set L. My second claim, H, K, and L are proper subgroups of G, and moreover, at most one of them can be trivial, at most one. And third claim, we have some type of the following thing. If I take two elements, H from H and K from K, their product happens to be in L. So HK and KH, they are both in L. It's true for every element apart from trivial elements. And similar claims, my third claim has three parts. Similar results can be proven by cycling through H, K, and L. So for example, for K in K, L in L, KL is in H, and LK is also in H, and so on. And finally, fourth claim, which is the main result, for every H in H, H squared is E, for every K in K, K squared is E, and likewise for L. So it's our plan. So give this problem a try if you wish, and I will see you in just a minute. Okay, so as I suggested, let L be G minus union of H and K union E. Notice the following. We can draw the following Venn diagram. So here is our subgroup H. Here we can write our subgroup K, for example. And finally, here is our subgroup, our set. We don't know yet if it's subgroup. It's L. Their only common element, it's pretty easy to see, is E. Well, why is that? Well, apart from E, no element of H or K can be in L. And moreover, it was our assumption that H and K have trivial intersection. So it must be like that. And these three sets, of course, give us entire group G. So our group G is partitioned by these three sets. Okay, first claim, proof of claim 1. Proof of claim 1. I wish to prove what exactly? I wish to prove that if L is in L, L inverse is in L as well. Maybe let's match the colors. Let's write it in violet. So proof of claim 1. Well, so let L be in L. Well, L inverse, of course, exists, and we have three options. First option, L inverse is in L. Well, there is nothing to be done. It's exactly what we want. This is exactly what we want. Let's tackle second possibility, that L inverse is in H, for example. L inverse is in H. Well, if L inverse is in H, remember that H is a subgroup. Since H is a subgroup of G, L inverse L, which is L inverse inverse, this is also in H. But remember also that L is also in, it's also, by our assumption, it's also in L. So L is in the intersection of H and L. So that implies that L is in the intersection of L and H. But if we go back, intersection is trivial, i.e. L equals E, and that implies that L inverse is also E, and of course E is in L. Finally, third possibility, L inverse is in K. We have, to be honest, the exact same reasoning. Since K is a subgroup of G, we have exactly the same type of reasoning. L equals L inverse inverse, and it's both in K and in L. So L is in the intersection of K and L, i.e. L is E, and L inverse is also E, and it's in our group L. That closes the proof of our first claim. Our second claim, very important one. We wish to show that KL and H are proper subgroups of our group. Well, they are for certain groups. How do I know that? Well, H and K are subgroups by our very assumption. They are subgroups. And L, remember, L is closed under the operation of G, but also it's closed under taking inverses. It was proven in claim number 1. So maybe let's write it. It's a proof of claim 2. Proof of claim 2. Proof of claim 2. Well, H and K are subgroups of G by assumption. And L is a subgroup of G by assumption and claim number 1. Okay, so now we know that they are groups. Now we need to show that they are proper. Well, H and K are proper by assumption, again, are not equal to G by assumption. And L, can L be equal J? Can L be equal to the entire group G? Well, if, let's write it in red because it's not possible. If L equals G, let's go back to the definition of our group L. L is G minus H union K union E. Well, that is only possible if both H and K are trivial. It's the only possibility for which L is our entire group G. Then H equals K equals trivial subgroup E, and it's contrary to the assumption because we assumed at the very beginning that our groups are different. Contrary to the assumption. Contrary to the assumption that H and K are different. So that means, in other words, that L is also a proper subgroup of G. Very well. And finally, I wish to show that at most two subgroups can be trivial. Well, at most, let's write it, at most one of K, H, K, and L can be trivial. How do I know that? Well, they cannot be. So why? Because H and K cannot be both trivial because they are different. Because different. So H cannot be equal K, cannot be equal E. It's impossible. So it's impossible. Let's write it in red. It's impossible. Well, for example, can K and L be trivial? Well, if K equals L equals trivial subgroup E, let's take a look. If they are both trivial, then looking back at our handy Venn diagram, if they are both trivial, then H must be the entire group G. Contrary to the assumption that H is a proper subgroup. Contrary to the assumption that H is not equal to G. And similar reasoning goes for L equals H equals E, then K must be equal G, contrary again. Contradiction again, once again. And that closes the proof of our second claim. So now we know that KL and H are subgroups, proper subgroups, and at most one of them can be trivial. Now, very important, claim number 3. Let's go back to claim number 3. I will prove only the first part because the second one and the third one are immediate consequences of the first one by cycling through subgroups. If I take two non-neutral elements, H in H and K in K, their product lands in L. So let's prove it. Proof of claim 3.A. So let H be in H but not E, and let K be in K but also it's not E. Well, then we have three possibilities. Let's consider three possibilities. First possibility. If hk is in L, well, that is what we want. Nothing to be done. That is what we want. Second possibility. Let's consider second possibility that hk is in H. Well, then we have the following development. Then H inverse is also in H. It's also in H. So H inverse HK, also known as K, is also in H. How do I know that? Well, if I multiply two elements of a subgroup, their product is again in our subgroup. So K is in H, but also K is in K. So K is in the intersection of H and K, but the intersection is trivial, it's E, and we have a problem, we have a contradiction, because we have assumed that K is not E. Contradiction. Contrary to the assumption that K is not E. Third claim, third possibility, HK is in K. Well, then we copy the reasoning. Then K inverse is of course in K because it's a subgroup. So H, also known as HK K inverse, is in K. And we have a similar story going on here. Also, H is in H, so H is in the intersection, which is trivial, which is again a contradiction. It's a contradiction. So only the first possibility is, well, possible. So HK must be in L, and also I leave the second part of claim A, I leave it to you, so prove the other way around, that KH is in L, and also I leave, as I said, parts B and C to you. They are very easy. Okay, and finally, so maybe let's write it. So parts, proofs of parts B and C are similar. So I close my proof at that point. And finally, the last claim, the most important one for us, I will only prove one part. I will prove part A, that if I take an element H in our subgroup H, its square is E. So proof of claim 3.A. Well, suppose to the contrary, that H is in H and H squared is not E. Well, then obviously H is also not E, because E squared is E. Moreover, now it's time to use our claim number 2. At most, by claim number 2, let's write it. By claim number 2, K is non-trivial or L is non-trivial. because we have demonstrated that at most one of these groups can be trivial. So without loss of generality, without loss of generality, for example, let K be in K, but it's not a neutral element E. Well, then by claim number 3, probably. Oh, sorry, I made a slight mistake in numeration. We are proving claim 4a, not 3a. By claim 3.a, since I have an element of H and an element of K, they are not neutral elements. HK is in L. HK is in L. Very well, very well. Not only HK is in L, but also H squared K is in L, because H squared is also not E by our supposition. But now notice that we have some kind of a problem, because notice also that H squared K can be written in another way. H squared K, it's H K, and now this is in L again, this is in H. And by claim 3.c, I believe, I have an element of H and an element of L. Let's go back. Yes, I have an element of H, an element of L. Their product lands in K. So it's in K by claim 3.c. By claim 3.c. And now we have a problem, because that implies that H squared K is both in K and in L, so it's E, i.e. H squared K equals E. And moreover, let's now take a look. Now we can take K inverse. So H squared equals K inverse, and H squared is in H. K inverse is in K, so H squared is both in H and in K. But again, their intersection is trivial, i.e. H squared equals in fact E, which was contrary to the supposition that it's not. Yes, we reach a contradiction. Contradiction. In other words, so supposing that H squared is not E leads to contradiction, so it must be equal E. Funny little fact. That means that for every H in H squared in fact equals E. Proofs of parts B and C are similar and left to you. B and C are similar. And hereby I close the proof of my final claim. And now notice that by claims 4a, 4b, And for C, since our group G is partitioned into H, K, and L, and in every case square is equals to E, we conclude that for every G in G, G squared is in fact equals E, and that finally closes the entire proof. Beautiful, beautiful problem. In general, algebra, in my opinion, is a beautiful branch of mathematics. Very elegant reasoning. And as I said, I am astonished by the fact that this problem was given to 12th graders in Romania. Astonished in a positive sense. I have nothing against giving hard problems to ambitious, talented students. I'm very curious because I have a feeling that mathematical culture in Romania is on a very high level. If you are a viewer from Romania, please tell me something about the level of mathematics in your country. I'm curious. I'm just curious. And yeah, so that's it. 4 claims lead to our main result, and that's it. Thank you for watching, and I will see you next time. Goodbye.